Welcome to clickmyproject.com. We are going to see the product for design and analysis of a highly efficient linearized CMOS subharmonic mixture for 0 and low IF applications. Next, we are going to see the abstract for our product. In translating the desired RF spectrum to 0 IF, there is no frequency problem, so that there is no need for expensive and bulky off-chip image rejection filter. This allows for the integration of the whole receiver circuit on a single chip to become feasible. One of the most challenging problems is the DC offset. A consequence of self-mixing resulted in the leakage of the signal from local oscillator to the mixture input. The LO signal is usually strong and usually leaks through the ever parasitic capacitances. The DC offset may cause adverse effects such as saturation of the next stages, noise, performance degradation, and non-linear distortion. Another issue is the limited dynamic range of the mixture that normally consists of many more components than that of LNAs, where they have to be able to process much stronger signals due to amplification provided by the latter. Therefore, mixtures are the main source of intermodulation distortion in the receiver chain, especially the second and third order intermodulation distortions. The solution to overcome the self-mixing and the DC offsets is the use of a subharmonic mixture, which uses one harmonic of the LO signal instead of its fundamental tone. In this case, multiplication of the LO signal by itself is prevented. It results in the elimination of the DC offset. The conventional LSSHM, the linearity is still a challenging issue, and receiver suffers from the second and third order intermodulations IM2 and IM3, which are the most important parts of nonlinearity at the output of the 0 IF receiver. Even order intermodulations do not appear at the output when the mixture is perfectly balanced. But in practice, there are some mismatches between the elements, such as threshold mismatch, transconduction mismatch. In our product, a new linearization technique for SHM is proposed. Next, we are going to see the flow diagram for our product. In the first auxiliary port, the IM2 product is mixed with the input signal to generate the IM3 signal. Then the IM3 signal is mixed in the main path. This reduces the overall IM3 in the circuit. The second auxiliary path, to cancel the total IM2 generated, low frequency IM2 product is amplified and then inverted. The input transconductance stage amplifies the RF signal and the accommodating stage switches the differential LO pair. The LO switching stage is actually a frequency doubler, which is employed to generate the even order harmonics, especially twice of the LO frequency. In a doubly balanced SHM, there are two pairs of LO switching transistors with different inputs to effectively provide switching at twice the rate of the traditional techniques. Assuming that the transistors are completely cut off when the gate voltage is below the threshold voltage, ignoring the subthreshold current, signals at each node of the output low frequency signal is obtained by mixing the drain signal of the LO stage with the RF input signal. The distortions performance of SHM usually specified by IIP2 and IIP3 is due to the nonlinearities in the mixer circuit. To design low distortion with mixture, before anything it is necessary to understand the nonlinear mechanism that causes distortion. The main source of distortion is the nonlinear conversion of voltage signal into current in the RF input stage. Finally, we are going to see the output for our product. We design the circuit in the Tanner. The cell SHM contains the design. The implementation of the RF transconduction stage of the proposed research along with the proposed cancellation circuit. M1 and M2 are the input transistors of the RO stage of the mixture. M1A, M2A and EZ1 compose a squaring circuit to generate a low frequency IM2 current. Since the drains of M1A and M2A are connected together, the odd order components of their currents do not appear in the sum of the output currents, and only the even order components are present, especially if the differential two-tone input signal is applied to the squaring circuit. The fundamental tones are cancelled at the output, while the low frequency IM2 current at omega 2 minus omega 1 remains. R and C are employed to convey high frequency RF and low frequency IM2 signals to the gate of M1 and M2. The parasitic capacitances of transistors M1A and M2A, which is a small signal model of IM2 generator, is obtained. The IM2 component generated at the drains of M1A and M2A is applied to a low-pass RC circuit, while a high-frequency RF input signal is applied to a high-pass RC circuit. The output signals in the gate voltage of M1 and M2 are the sum of high-frequency RF signal and low-frequency IM2 signal respectively. The circuit consists of the RF transconductance stage, LO switching stage, and the output load stage RL. To improve the linearity of the mixture, the proposed cancellation circuit in the RF transconductance stage, including M1 to M5A, is also added to the RF stage. The conversion, gain, bandwidth, and noise performance of the mixture are affected by the parasitic capacitances between the RF transconductance pairs as well as the switching pairs. For tuning out the parasitic capacitances, an inductor is employed between the RF and LO stages, which utilize the pi network. The effect of the cancellation circuit on the pi network on the complete mixture is based on the ultra series analysis in the harmonic input method. To create a new project, we have to click on the file and then give the new. Then to create a new cell, click on the new and give the new view and specify the folder to which you have to save your project. Then for the simulation result, we have to click on the setup and give the spice simulation and add the library files and click on the transient Fourier analysis, which is 600 nanoseconds for the start time. Maximum time step is 1 nanosecond. Print start time is 0. Print time step is 1 nanoseconds. Then click on OK. Then click on the run. The waveform will be generated. This is the waveform for the input. We see the waveform in the WEdit waveform Weaver. Thank you.